Yes, Ryan, you can start the recording.
Done.
And it is my pleasure to introduce today's speaker. It will be Kasso Okoudjou from the Tufts University. So Kasso will tell us about the completeness of Weyl-Heisenberg positive operator valued measures. So Kasso, please, we're all
Thank
ears.
you. Thank you very much. And thank you for the invitation. And thank you for accommodating me to talk at a different time than your usual time. So this is going to be a joint work with Asaf Goldberger and Shuji Kang. Many of you probably know Shuji. She was my graduate student, and she's now a postdoc with Keaton in Texas. I think Shuji is also giving a talk later this semester. So you can view this as somehow like setting up like what she's going to talk about. I will not sort of provide too much detail, and hopefully by the time Shuji give a talk, there'll be more detail. You can stop me anytime. And here's the plan of the talk. So I'll tell you what I call finite Gabo POVM or Weyl-Heisenberg POVM. They are related to the theory of Gabo frame, especially in this finite dimensional setting. I cannot sort of give a talk without sort of going to something that has been like near my heart for many years, the P-frame potential. So I'll have like a slight detour on that problem. I know many people on this are interested in that problem. And I'll try to connect it to somehow it's connected to the Gabo frame on infinite dimension. And the bulk of the talk is actually a question that we start asking ourselves a couple of years ago about the completeness of this. So by completeness, I'm not talking about completeness in terms of the vector spanning like CD. I'm talking about the completeness of the corresponding rank 1 operators or rank 1 matrices. Can this span the set of D by D matrices? And I'll share with you some of the observation and some of the things that are emerging from our work. Most of the example that I'll talk about will pretty much be in dimension 3. I'll mention a few in dimension 4 and 5, but even in dimension 3, it seems like this is actually not a simple thing to completely classify. All right, so just to, okay, I thought I fixed all of this, but you can already spot a typo here. So there's a first typo, I thought I fixed it. So a Gabo set, I forgot to divide this by D. So otherwise it's not going to make sense. So the set of time frequency shift of a unit vector, here I'm going to assume that G is a unit vector in CD, is going to be called the Gabo system generated by that vector G. So this is just like a take G, multiplied by all the modulation. The modulation is just like your usual matrix with the root of unity on the diagonal. And T is just a translation matrix. So it's just a shift operator, 0, 1, and then you just sort of rotate this cyclically. And I'll take powers of this matrix, and I'm going to call the system that I get in that fashion, I'm going to call it a Gabo system. Now, it turned out that given any G in dimension D, if you normalize it to be a unit vector, then this Gabo system automatically what we call a FUNTF. FUNTF stands for finite unit norm tight frame. So finite unit norm tight frame, that's what this means. And this is the definition of finite unit norm tight frame is given in this setting. So I have n vector in dimension D. I normalize them so that where the unit norm comes from. The finite means that I'm working in finite dimension. And the tight frame condition is exactly expressed in this fashion right here. It's this equation. It just tells you that you have pretty much like an expression almost similar to an orthonormal expression, except that you're paying a price, and the price that you're paying is that your system is most likely redundant, and you have to sort of have this factor over here. This is equivalent to have something also very similar to Parseval equality, and that's what the second statement is saying. The other equivalent condition is this last one, and this quantity is actually a sort of an important quantity, which I'm going to talk about like a little bit below, and it usually comes with frame potential. It was introduced probably in the frame context by Benedetto and Ficus, but this community probably knows it a lot. I think there are some work earlier by I think Selnikov, I believe, in the 70s, where this notion of tight frame was already sort of introduced, and the characterization of the minimizer of the frame, what we know today as the frame potential, was already established. By the way, there is this, I think Strikas once told me that everything in math is named after the third person who discovered it. So the frame potential is sort of referred to like by Benedetto and Ficus, but I think they were, it was probably like introduced a little bit early. So there is another thing that I want to mention, which is to say that the FANTF is going to be called equiangular. So that's the term equiangular tight frame. If in addition of being like a FANTF, like a finite unit non-tight frame, it also satisfies this condition that the different inner product, at least in absolute value, are all constant, okay? And so this is going to be an important thing to keep in mind. So the theorem by Benedetto and Ficus, and I guess I should have had like a few more authors who have sort of discovered this a little bit earlier, is to say that a set of vector, n vector in dimension D is a FANTF if and only if it's a minimizer of this functional right here. So this functional somehow like measure how orthonormal your set is. And if you have more vector than the dimension, clearly your set will not sort of be orthogonal. But if you have more vector, then what's going to happen is that these vectors are going to push each other to a point where they're going to minimize exactly this quantity. And that will give you exactly the FANTF that I just sort of defined earlier. So a way to check that something is a FANTF is just to check if it sort of reach the minimum value. And I didn't sort of put the minimum value, but this is always greater or equal to n squared divided by d, especially assuming here that n is greater or equal to d. When n is less than d, then the only way to minimize this is exactly when you have an orthonormal set of vectors, okay? But I'm going to work mostly for n greater or equal to d, so that's why I don't have to worry about like just like things that do not span the entire set CD. All right, so I was going to talk a little bit about the frame minimization problem, but this is actually a very simple minimization problem, because once you sort of have like a frame of a vector x1, s2, all the way to xn, you can put this into a matrix S, into a matrix C, that you usually call, let's call it C star. And if you, I think I'm going to call it, I'm just going to call this matrix maybe D. And if you form the matrix, which is S is equal to D star, it's a positive definite matrix, and the frame potential FP2 of N D of S is actually nothing but the trace of the square of D star multiplied by D, the trace of this matrix. And from there, you can actually just sort of see that this has to be like the sum of the eigenvalue of S square from 1 to n of lambda k square. And what you end up doing is to minimize this under the condition that the trace of the lambda k is equal to the number of vectors that you have. This is D. And you see that the minimum will occur exactly when all the eigenvalue of this matrix are exactly the same. And that's how you end up with this equality that you have either here or this version that you have over there. Okay, so that's an easy way to sort of get like the frame condition or the tight frame condition. There is another quantity that's important, and that one is related to the ETF part that I mentioned. This is the famous Welsh bound that says that if you give me any n set of vector in dimension D, their unit vector, then if I look at the maximum correlation between them, so I look at the angle between SK and XL when K is not equal to L, and I try to minimize this quantity, then a lower bound for that, it's this quantity here that usually referred to as the Welsh bound. And equality hold if and only if we have an ETF. Now, ETF do not exist all the time. They are conditioned on the number of vectors that you can have depending on the field in which you're working. So we're working here in the complex field. So the maximum number of vectors that you can have is exactly D squared. And when it's exactly this square, we're going to sort of reach like the Zauner, the White-Heisenberg system, because those are easy to generate. But I'm going just slightly ahead of myself here. Just want to sort of point out that by looking at the potential, the frame potential of Benedetto and this one, which is the Welsh bound, you can actually define a family of potential, Fp n, that we call the P frame potential, and that many people here have been interested in sort of investigating. And you might want to sort of see what are the configuration in a given dimension that minimize this object. This is a very interesting problem. There are some very interesting work by Alex, Dima, Ryan, I think Josia Park, that sort of have sort of produced some very interesting thing about like some of the configuration that sort of minimize either this frame potential or the continuous version of this frame potential. So I always like to sort of put this up. This was for a long time like something that fascinated me. Like here, this curve right here at the bottom is the curve that gives you the function of the minimum of the frame potential as you vary P from 0 to infinity in dimension D equal to 2. And with n equal to 3 vector, which is just the dimension plus 1. So that curve was a problem that Martin Euler and I will work on back in, I think, in 2012. And we were able to find that for 3 vector in 2 dimensions, the minimizer what we call orthonormal basis plus 1 vector. And there are just 2 families that minimize these things. So the equiangular tight frame that we call the Mercedes-Benz, which is essential like the 3 root of unity, are going to be the minimizer from this point all the way down. And at that point, we conjecture that all the other minimizer will look like the curve that are above here. So for many years, this remained like open. I think Alexei at some point was able to, with Josia, they were able to push this a little bit, especially in the range over here. And very recently, the complete proof of this conjecture or this observation that we made with Martin Euler was completely established. And it was established by Zhu and Zhu in 2020. And they completely gave a way to actually get the minimizer in this setting. But this is just one example of many problems related to this potential that's still open out there. And I'm just going to sort of mention that even in dimension 2, when you have like n to be arbitrary, the most recent work by myself and Shuji, Gonzalez, and Goodman, and Shumation make some progress on this problem, but there are still some very, very small, what I view as a small interesting case, but where we think we know what the minimizer should be, but we have not been able to establish any concrete result in this direction. I think Dima and Alexei and many other people here have like some conjecture about the relationship between the minimizer of a continuous version of a frame potential and the discrete potential here. And I think it's a very interesting problem, and I hope like somebody sort of keep looking at this. But I feel like I could not sort of give a talk without sort of reminding people that this is still something very interesting that still need to be solved. And in particular, the dimension 2 case, it seems to sort of be like quite embarrassing that we don't know how to completely settle this problem so far. So if anyone wants to sort of play a little bit with this, go ahead. Okay. All right, so the reason why I actually make this connection is not that I just want to talk about it, but it's actually because you can actually look at the frame potential, but decide to restrict it to a very special class of function or class of vector. In this particular case, I'm going to restrict it to, I'll fix the function G, and then I'll take what I just call Gabo frame that's generated by this. I'll look at K, and then TL of G. I'll take all the translation and all the modulation, and then I'll just compute this. This becomes just a function of only one variable in a way. It just becomes a function of a generator. And the question is this a little easier to minimize in a way? And it turns out that you can prove, and this is not too difficult to establish, you can prove that the minimum value of this, at least the lower bound, is this quantity right here. And that lower bound is achieved exactly if and only if I think I miswrote this. It should be G. I have not defined anything like pi. If and only this thing is not only a Gabo tight frame, but it's actually equiangular, meaning that all this inner product must be exactly equal to each other in order to get like a minimizer for this. But we don't know if those vectors exist, and that's exactly the sort of the purpose of this presentation. Like what happened for vector G in general when you don't necessarily know that you have all this inner product to be equal to each other. So the beginning of the problem that I'm about to talk about is actually like whether or not we can always sort of find this ETF. This is the Zauner conjecture. But in the absence of solving the Zauner conjecture, are there other interesting things that we can take out of the system that are already very nice? Because given any vector, I know that the finite Gabo system always form a tight frame. And the question is, are there any other interesting property that this Gabo system have if they are not equiangular and therefore solve the Zauner conjecture? So just to sort of highlight briefly, like why the Gabo system are automatically a tight frame, this slide should have come a little bit earlier. It's just based on the property of the DFT. So you just write out like this expression. And you can easily see that if you look at the inner product of any vector with your Gabo vectors here, and you square them, you look at the norm of this, then you get exactly a multiple of the norm of your function. This is pretty straightforward. So there is nothing difficult in proving that given any arbitrarily unique norm function, then the finite Gabo system that you obtain is actually just a tight frame. So this is pretty easy to establish. Now, the Zauner conjecture that was put forth like by Zauner in 1999 said that for every dimension, there exists a unit vector so that the Gabo functions that I just defined earlier are also equiangular. In other words, the inner product between any two of these vectors is exactly equal to 1 over the square of it is exactly a constant. And you can check that the value of that constant is exactly 1 over d plus 1. This is exactly going to be the bound, the Welsh bound that I mentioned a little bit earlier here. If you look at the Welsh bound that I mentioned here, where is the Welsh bound? Okay, I don't see it. Okay, right here. If you take n to be equal to d squared, then the quantity that you obtain is exactly the number that I have for the equiangular tight Gabo system that's here. So Zauner conjecture, if it was true, will give us a set of d square vector in CD that are going to be exactly achieving the Welsh bound. That one interpretation of this. So there's been a lot of recent work about on this topic. Appleby, Flamia, Grassol, Wren, Scott. I think some of them might have sort of given a talk here or sort of a talk like close to this at places where we've seen this recently. So my goal is not to actually worry about like solving the Zauner conjecture. My goal is to sort of see what happens when you might not be able to get equality here. Can you find vector where the number of inner product that you have is not too big? Can you find G where you only have maybe 2 inner product or maybe only 4, or given the dimension, you don't want to have too many inner products. You have to also see that there is a lot of symmetry already built into the DF, into computing this quantity. So there is an easy combinatorial argument to see how many distinct inner product you can get to begin with. But the question is, can you make that number low rather than having exactly 1 as predicted by Zauner conjecture? If I want to generate something that has only 2 different inner products, is it possible? And can I characterize with vector G that sort of generate that system? That was actually what sort of motivated all this problem that I'm about to talk about. And I'll spend my time on doing that. So to set the proper framework, rather than looking at the vector, the Gabo system, I'm going to look at the rank 1 matrices generated by each of these vectors. So I'm changing the problem. I start from a vector G. I construct this tight Gabo frame, but rather than looking at the tight Gabo frame, I'm going to look at the rank 1 matrices that each of these vectors generates. So it's going to give me a family of D square rank 1 matrices in CD. And what I really want to sort of know is whether or not this system is linearly independent in the set of D by D matrices. And there is a very nice terminology to sort of capture all these notions. So here again, I make a mistake. There is a typo. I need to divide this by D. So from now on, I'm going to focus on this family. Pi KL will just be the rank 1 associated to each of the GKL. And I'm going to sort of make some definition. It sort of easily follow that if you take any subset of ZD cross ZD and look at just the sum of all those rank 1, where the index are inset, what you get is going to sort of be a positive semi-definite matrix. And the map that sends like it's set to such a positive semi-definite matrix is called a POVM, positive operator value measure. It's not important to sort of remember this terminology. The key point is that the tightness condition tells you that if you add up all these rank 1 matrices on the entire set, you get essentially the identity matrix. That's exactly the tightness condition that we stated earlier. That's what being a FONTF is exactly about. There is another property that's some POVMs share. It's called symmetry. And the symmetry condition is just a statement that if I look at the inner product of this rank 1 in the Frobenius inner product, then you have a constant. It turns out that if I have a Gabo ETF and I look at this inner product is exactly the quantity that I have over here. It's exactly the square modulus of the inner product between G and a time frequency shift of G by different K and L. And so the symmetry condition in general for a POVM is just a statement that this inner product give you a constant value as KL is different from K prime L prime. And now the last part, informational completeness or informationally complete, is just a statement that this is a complete set in the set of D by D matrix. Now, when you have a symmetry condition, when this is true, then you automatically get the condition that is complete. But you might be complete without being symmetric. So from now on, I really want to focus just on the completeness part, okay? When do we have a vector G that's going to generate a complete set of D square matrix of rank 1 in dimension D, okay? So that's the problem that I want to sort of focus on from now on. By the way, so it's not too difficult to see that having the symmetric condition give you completeness, because in that case, if you look at the Gramian matrix, which is what we're going to look at in a bit, the Gramian matrix is just going to be a matrix with a constant diagonal, and then all the other entry will just be exactly the same. So you can just sort of use like, it's going to be a sequential matrix, so you can just essentially diagonalize it with the DFT matrix, and that's a way to sort of see that. As soon as I have like a symmetry, then completeness follow easily. And therefore, what I'm trying to do is to see what happens when I don't have a symmetry. And I want to discuss completeness. So that's the main question that the talk is going to focus on, completeness of these rank 1 matrices. I'm going to focus on the Gramian matrix. It's a positive semi-definite matrix. So I want to see when the smallest eigenvalue is strictly positive. There have been a lot of questions about this kind of system in the literature, but sort of coming from a different point of view. The one that comes to my mind is a work by Gutfender, Jim Lawrence, and David Walnut, where they're looking at not looking at the linear independence of this rank 1, but rather they're looking at like vector G, for which if you look at the Gabo system that's over here, so here again, I need to divide by D. If you look at this Gabo system, you want to understand the linear dependency among these vectors, okay? And for those who know a little bit about like the HRT conjecture, this is almost like, it's not exactly, but it's almost like a finite dimensional vector, a version of the HRT conjecture. By the way, I already know that this has to be always linearly dependent. I have more vector than the dimension. Therefore, the question is, what are the subset? What the size of the larger subset that will be linearly independent? And what Walnut, Founder, and Lawrence prove is that if D is a prime number, then in general, if you give me like, you can find like a set that's dense in CD so that for any vector G from that set, if you consider this system of vector, then any D of them will become linearly independent. That's what the statement that I just made there. But again, we're not investigating the same problem. Our problem is not concerned with a vector G, but is concerned with the rank 1 matrices that we obtain from this Gabo system. All right, so because Gramian of this thing is not so difficult to compute, you can actually get easily like the following statement. So for any vector G in CD, if I sort of normalize the vector, then the gram matrix of this rank 1. So now I'm looking at rank 1 and I'm looking at the gram matrix in the Frobenius inner product. You can prove that this gram matrix is actually like a block circulant, and each of the block in your each of your subblock is also a circulant matrix. And in fact, the entry are exactly the square of the inner product between G and the time frequency sheet version of G. And it's explicitly given by the formula that I have over here. The second thing that you can easily see is that G can be completely diagonalized by the DFT. You have to sort of make the DFT the appropriate size. That's where the tensor product is it's meant to be here. And you can explicitly compute all the eigenvalues of this gram matrix, and they are explicitly given by this formula right here. Now, we already know that the eigenvalue are non-negative, but in fact, you can write them. They're going to be like a square modulus of a polynomial, or in other words, the short-time Fourier transform. So the object that you sort of see here is nothing but G inner product e to the power 2 pi I bn divided by D, and then multiply by G, and then you shift this by A. That's what this is. So these are just the inner product of the Gabo frame or the Gabo vector that you have. So the eigenvalue are something that's pretty simple to compute in principle. And you can always prove that the rank of this matrix G is going to be at least D. So in other words, this rank 1 matrix is always going to span a linear space of dimension at least D in the set of D by D matrices. And when the dimension is odd, you can also prove that the rank can only take odd value, so it cannot take any even value. So it can take any odd value between essentially D and D squared. So the proof is, I'm not going to go over the technical part of the proof. The proof, it's straightforward. You just compute this inner product, and then you can rearrange it to sort of see that the matrix is going to be block circulant, and each of the block themselves are going to be circulant block. Okay. The other thing that you can see is that the eigenvalue have some sort of built-in symmetry. They come almost sort of in pair, and these are the pair that you have over here. The very first eigenvalue is easy to compute. That's exactly going to always be the dimension of the vector space that you're using. And you can easily prove that if the rank was less than D, then you see that the trace of G will not be what you should be getting. And that's how you prove that the trace has to be at least D. The other part about the fact that it's odd, just follow by doing essentially the same trace analysis and realizing that the eigenvalue actually come in this pair form right here. Okay. All right, so the question that we were asked to solve actually had a pretty simple answer. The Gabo POVM is going to be complete if and only if all these inner products are exactly non-zero when A and B is not equal, for any A and B in ZD called ZD. Well, the reason is that these inner products are essentially exactly the square of your eigenvalues of your gram matrix. And when each of them is non-zero, then the matrix is going to sort of be positive definite, and therefore the rank of this system is going to be D. So the question is, when do we have that? It turns out that this has sort of been like work done in the 90s by Denny Healy and Chorek, and also by another group, Dariano, Peritino, and Sachi in 2004. They work with more general POVM, and they arrive essentially at the same conclusion. So if you read their paper, you'll see that at the end, what they got is that if I have a POVM that's generated by Gabo type system, then it's going to be complete exactly when all the inner product among my Gabo or my atom are non-zero. So this is not a new result. It's been known for some time. So you can sort of use this to make the following statement that it's somehow like a little bit boring to be looking at complete POVM. And you should actually sort of try to find things that are not complete. And the reason I'm saying this is that being a complete POVM is actually a generic quote unquote property. By what I mean by generic, you can prove that the set of complete POVM in the Zariski topology is dense, and therefore pretty much every vector that you take almost randomly will sort of have a property that is going to sort of lead to a complete POVM. The difficulty about like the Zauner conjecture is that you're not only looking at something that's complete, you're actually looking at something that, in addition to being complete, is also symmetric. So here, this is exactly where the difference between, if I'm symmetric, I'm automatically complete, but I can be complete without being symmetric. And it's way, way easier. What this theorem is, or this result is saying, it's saying that it's way easier for me to put my hand on something that's complete. Now, how do I sort of make sure that that thing is also symmetric? That's a different story. So in a way, we shouldn't be looking at things that are symmetric, that are complete. Things that are incomplete seem to sort of be like hard to put your hand on. And that's what I'm going to spend the remaining part of the talk to sort of focus on. So the first question that I want to sort of try to look at is, if you give me an incomplete POVM, so here some of the inner product can be equal to 0. That's what this means essentially. So you give me a POVM, it's going to be tight. To be incomplete means that some of the inner product are going to be 0. The number of non-zero inner product is exactly the rank of a dimension of a linear span of this POVM. So the question is, what are the possible dimensions of this linear span? Can we, given a P between D and D squared, I already mentioned that when D is odd, there is no way you can get something that's going to sort of be even dimension. But in general, if I give you a D that's odd, can you sort of ensure that I have like for every P in that range, that I have a G that's going to generate like an incomplete POVM for that given dimension? And that's the type of problem that we're trying to do. As you can imagine, we have not been able to completely classify this, but in dimension 3, I think we've been able to completely settle this. And we have some pretty good example in over dimension. There are some generic statements that we can make. And I'm just going to focus essentially on the dimension 3 case, and then just sort of share with you some example that we've been working on. And that's going to lead us toward the end of the talk. I do need to mention that another recent work by Joe Iverson, John Gasper, and Dustin Mixon, they look at POVM that are not generated by rank 1 matrices. So rather than looking at like GK, tensor GK, they look at like POVM that are generated by overthink. In particular, they look at POVM that are generated by rank 2 matrices. And they have results that's sort of similar to ours, but it's actually in a completely different direction. So it's related, but it's not exactly the same sort of result. The only thing that sort of relates the two is that there is an underlying algebraic property that seems to sort of be at play here. And I'm going to mention something about it toward the end of the talk. And that seems to sort of be the only relationship between the result that they obtain and the sum of the result that I'm going to present here. All right. So all right, so for dimension 3, it's actually not difficult to sort of see what all the eigenvalues of this rank 1, the gram matrix of this rank 1 matrix is going to be. So remember, for dimension 3, I have exactly 9 rank 1 matrices here by KL. If I look at the gram matrix, then I can sort of write down explicitly what the eigenvalues of those are. And these are the eigenvalue that I get explicitly. So to sort of determine the rank of the system that they generate, all you have to worry about is among these, how many of these are going to be equal to 0? That's what you sort of trying to understand at the end. And you can sort of already see what's going on. So if you remove this one, what you're looking at almost like the correlation of G with one shift version of itself, and you're looking at the Fourier coefficient of that vector, and you're looking at the square. So at the end, this become, at least in this small dimension, a pretty simple problem to sort of look at.
Was der für ein Vortrag hält? Ohne Scheiß.
I'm good? Yeah, okay. Thanks. All right, so what I want to sort of look at is that at the end of the day, this is what we're striving to look at. I give you a vector G. I'm going to look at G with multiplied by its translation. So I put a dot here, it's not a dot product. All I'm saying here is that I'm just going to do the entry-wise product here. And I'm looking at the 3x3 DFT of this vector. And I want to see when the 3x3 DFT of this vector is equal to 0 and when it's not equal to 0, and classify as much as I can what vector I get. So for dimension 3, this is essentially the complete classification. If the support of your function is G, so if your function G has only a single entry, then the POVM that you get are always going to be rank 3. So remember, I'm working in the odd case. The rank can only be an odd number, so it can be 3, 5, 7, or 9. Okay. To be 9, that's a case where it's the system is complete, and generically, I just told you that those are always sort of available. And in fact, any vector of support 2 will always give you something that's going to be complete. So no matter what vector G you take in 2 dimensions, and sorry, in 3 dimensions, if there is exactly 2 non-zero entry in your vector, then you can guarantee that the POVM that you obtain is going to always be complete. But it's going to be symmetric only when the vector has this form, okay? Or of course, you can take permutation of this. So there are some operations that you can take that's going to sort of leave this whole problem invariant. So I'm not going to worry about that. I'm going to list some of those operations toward the end of the talk. So essentially, these are the vector that you're looking at. Now, I don't know if any of you sort of have looked at the Zauner conjecture. This family of vector for the Zauner vector is one of the known vector that generate like, that solve the Zauner conjecture in 3 dimensions. And it happened to be like one of the cases for which you have complete symmetry. But if I change the form of a vector and just put a G0 here and a G1 here, and then a 0, with the condition that G0 square plus G1 square is equal to 1, then as long as G1 is not equal to G0, then I'm not going to get something that's going to be symmetric. So that's actually, to me, was actually a surprise. I was not expecting this. So I have this family of things that are going to be symmetric, and it happened to be like a symmetric exactly for just a single value here, not like an entire family. So that was something surprising that we discovered along the way. And the proof is not terribly difficult. You can just sort of do this easily. So just look at, again, the key thing is this correlation between these 2 vectors. You want to sort of understand the support of G when you compare it to the correlation to its shift. And in this particular case, with the structure of this vector, then you can easily see that the result is going to follow. Now, the most interesting case, as you can imagine, is what happens when the support of a function is full. So when the vector J has a full support, then that's where you sort of have like a lot more things to sort of say. So remember, support 1, I can never be complete. I can only get rank 3. Support 2, I'm always complete. Now support 3, I can pretty much sort of get like pretty much a lot of things. So here essentially the complete classification when the support is when the support is 3. Again, there are permutation, there are operations that you need to sort of apply to leave this property invariant. So up to those property, the vector that are going to sort of give you like a rank 3 are listed in this set over here. So if you add that to a vector with one support, then you get completely the classification of all vector that give you rank 3 POVM. And there is no rank 5, and I'll show you on the next example, like something about rank 7. Rank 7 is something that we have not been able to actually completely classify. I think we have some partial result, but a complete classification of this is not something that we have at the moment. Now, there are operations that sort of leave this whole thing invariant. So multiplication by a constant vector. So I start from a vector G, and I multiply G by a C, where the modulus of C is equal to 1. Then this whole property that I just talked about will not sort of change. If I sort of take a translation of G, if I know the rank of a G that's something that's generated by G, then if I go to H is equal to a sort of shift of G, then this is also not going to sort of make any difference. Some scaling, or you can view this as a multiplication as well. I can sort of scale or sort of upsampling or downsampling, depending on how you view this. This is also going to sort of leave this whole property invariant. And there are some quadratic shifts that are also going to come into play that can also sort of leave this whole property invariant. So I'm going to sort of show you some examples. So this is one example where I have complete, and I have completeness, but I don't have symmetry. So this is a gram matrix that you get in this case. Observe that the diagonal, because I scale it, is exactly 1, but the off diagonal are just like essentially 2 numbers, like 3 and 7. And that was a question that I started from. The question that I started from is that, suppose you know that you can solve Zauner conjecture. Can you actually find a class of vector where you know you can guarantee that there are not going to be that many inner products in your system? And this is a family of examples that you can actually generate this way. This is a complete POVM. The only thing that's missing to solve Zauner is that it's not symmetric. But on the other hand, the number of distinct inner products in this system is pretty small. There are only 2 here, and I can sort of generate a bunch using the result that I just sort of mentioned to you. Sasha Bag, myself, and Alexei worked some years ago on something that we call 2-distance tight frame. This is not going to generate, I mean, I'm talking about something where I'm taking the modular square here. This is not going to generate like a tight frame. On the other hand, this is a Gramian matrix of a system of 9 vector where you only have like a 2-distant value, essentially. So this is a sorry, that's me, but that was not my kid, so sorry about that. So that's the risk that you take to leave your phone on for your kids. So I'm sorry about that. All right, so what I was saying is that this is actually one of the motivating examples that we were looking at, being able to find things that do not solve Zauner, but still share pretty much all the property of Zauner, except that all the inner products are not the same, but they take only small value. And I look at this somehow as an example of a 2-distance set or 2-distance frame, a frame where when you look at the inner product, at least in absolute value of all the entry of the vector, then you get only like a small number of value. So there seem to be a lot that you can sort of do in this direction that we haven't sort of done yet. This is another example. So this one clearly, because once you sort of start seeing 0, you're not complete. So this is not complete. I think it's only span a rank 3 in this case. And again, it's an example of 2-distance again, because there is only 0 or 1 as a value. So there are other examples that I can sort of put down. I will just sort of try to wrap up here by mentioning that the problem seem interesting, but seem also difficult. So here is we've been sort of deciding to choose what kind of question we want to essentially address. And for instance, classifying like a thing that generates a subspace of dimension D, that's something that we know we can completely do now. And hopefully, Shoji will sort of talk a little bit more about that when she gives a talk later in the semester. But in general, it seems like if you give me like a targeted dimension, trying to sort of prove or disprove that you have an object of this kind, it seems to be a little bit difficult at this point. So not exactly sure how to sort of handle the general case, but there's some sort of very interesting algebraic property that are sort of at play here that we hope we can explore a little bit more. Now, you recall that I start the talk at some point by talking about the frame potential, and I restrict the frame potential to the Zauner vectors. And we recall that this thing were minimized exactly when I have an equiangular tight frame. There is actually a quote unquote an easy proof of this fact, which goes as follows. Remember, the Gramian of this has eigenvalue exactly the square of these numbers. So essentially, what you're looking at here is just a trace of this Gramian matrix to the power p over 2 up to a constant. So you're trying to sort of, what you're really trying to do is to somehow like minimize something of this form, subject to the condition that the sum of the lambda k is equal to a constant. I don't know, something like d squared. And the only way this is going to sort of be minimized is exactly all of the eigenvalue are going to be the same. But there is a catch here. Yes, I know I can always do this minimization, but the problem of minimizing this is actually a little bit different. You need now to sort of sit down and see whether or not you can find a vector G where each of this common eigenvalue will be the value of all this inner product. And that takes you back to the Zauner conjecture. So at one point, what we were trying to do is whether or not you can actually conclude that the minimizer must always be complete set, or whether or not the minimizer will sort of have like some zero inside. That question is still a question that I don't know how to answer, but it seemed to me that at least for P even, it looks to me that the minimizer should always be complete. In other words, none of this inner product should be zero if I'm expecting to sort of be a minimizer. In fact, for all P greater than 2, technically, whenever the Zauner conjecture is solvable, then I know I reach the minimizer, and all those things are exactly complete. So there's a relationship between the completeness and the minimizer for this, especially when the Zauner vector do not exist. This will be something more interesting to look into. So I'm going to sort of wrap up here. We hopefully will have like something out by the end of the semester. If you want to learn more about the Zauner conjecture, this is one of the main paper. These two will give you a very good broad overview of the known result. I think there've been a lot more new results. If you look at Appleby or Marcus Grassol recent paper, you'll be able to sort of see a lot of new things. The paper by Joey Iverson that sort of closely related to some of the things that I talked about today is this one right here. And Dennis Healy paper and Dariano paper are the paper, at least the only two paper where I know for sure that the result about the completeness of this Garbo type POVM was already established. It might be that it exists in other literature, but these are the only two that I've been able to track down. And all the other things about the frame potential are somewhere in all of this. So with that, I would like to thank you for the opportunity to give a talk here. I'll be happy to answer questions. And thank you very much.
All right, thank you, Kasso, for the fascinating talk. And let's open the floor for questions. So do we have any questions, comments for the speaker? Yeah, okay, so maybe just to sort of start the ball rolling. So in dimension 3, so these examples that you looked at, so you could use the fact that, okay, there exists this system that is known to achieve Zauner's, to achieve Welch bound and to basically realize the Zauner's conjecture, and it was known to be Gabor, right? So are there many other instances where it is known that the Zauner system, so to say, well, okay, so the one that achieves Welsh bound is Gabor system.
No, so okay, I think I understand. If I understand what you're saying is, so the Welsh bound question, right, or the question about equiangularity in general, it's a broader question. And when you specialize the question to vector that are generated by like the action of these matrices, that's when you get like the Gabo type vectors.
Yep.
And the Zauner conjecture is exactly whether or not you can sort of find a vector that sort of achieve like saturate the Welsh bound.
Yes.
So in dimension 3, Zauner conjecture is pretty much, we know all the family of vector that sort of satisfy like solve the Zauner conjecture in dimension 3. You can write them explicitly down. Okay. The question that we are addressing is slightly different. We want to sort of not necessarily look at things that are complete. We were actually looking at things that are incomplete. And we try to classify all possible vectors in dimension 3. What are the rank of the POVM that they generate? If they generate something of dimension 9, we're pretty much already close to the Zauner case. So our goal at the beginning was actually to sort of stay a little bit away from that. So I'm not sure if I...
Yeah. So I was thinking, so Gabor is just like one system, one way to generate a system vector. So you start with G, then you shift here and shift in the frequency domain. So so you get a system. But in general, this is not going to be a solution of Zauner. At least you don't know, you will get exactly the right n squared and it will be the right system. So, but in 3, if I understood correctly what you said, in 3, it is known that you can take a certain Gabor system and it will achieve Zauner's bound, Zauner's,
exactly.
Right? So other cases, other dimensions, is it known that, okay, in this other case, you can also take a Gabor system, it will be optimal? No.
So that's a completely open question. So I think to date, I don't remember the exact dimension for which it's known that you can do it, but I believe like you can prove that up to dimension 45, except maybe some few dimension in between, that you can always find a vector that's going to sort of be like a Zauner vector. And then beyond that, there's been a lot of numerical work that show that, okay, potentially you have them, but it hasn't been completely proved that they do really like solve the Zauner conjecture. But your question, if I understand, is if the Zauner vector exists, then it will solve the equiangular type problem, right? Equiangularity problem. But you might sort of still have like solve this equiangularity problem without the solution being of a Gabo type.
Yeah,
that's
exactly.
What you say.
Yeah, exactly.
Exactly. And for that, I don't know. I've been sort of looking at this from the Zauner angle mostly because that's something that I'm sort of naturally led to. But it's really possible that the Zauner conjecture could be false, but you can still be able to construct vectors that are going to achieve the Welsh bound in complex dimension for exactly D-square vector. But I've been focused more on the Zauner part because it's more related to Gabo system.
Right. I think also, okay, so I don't know. I don't want to sort of, so I know I have questions. I have many questions, but I don't know. I don't want to sort of occupy.
Sorry.
So Dima, go ahead.
Yeah, if I can intervene, just elaborating on your question. I think it's also an issue of terminology because if you look in various literature, I think some part of the literature states the Zauner conjecture precisely as Kasso stated, as you stated in your talk today. But sometimes it's just stated that there exists a sigpov of that there exists an equiangular set of size d squared without specifying that it has to be a Gabor frame, that is just an arbitrary equiangular set of d squared vectors in CD. So in this sense, I was also wondering, are all the known examples of these sets of Gabor type, or I mean in higher dimensions especially, and even the ones constructed numerically, or do there exist dimensions where you have examples, or at least numerical examples, which are not of Gabor type?
If I remember correctly, I think Appleby and Grassol have example, that's still like it's an action, but not necessarily under the Heisenberg group.
Okay.
And the Gabo one are action under the Heisenberg group. So I believe there are some examples where the action is not under the Heisenberg group, but not that many. And I do believe like most of the numerical example that they are looking at is exactly a vector that are going to be like generated from the action of the Heisenberg group.
Okay, thank you.
Yeah, that's pretty much yeah. That's also exactly what I meant as a question. So, do you ever? When is it that you know that it is Gabor action that gives you the optimal system? Exactly. Yeah. Yeah. Okay.
I think so. Yes, and I think as Dimitri mentioned, yes, the question about like the existence of this sick POVM is a broader question, and Zauner conjecture is exactly the way I stated it. He wants to sort of see it as an action from the Heisenberg group, or more precisely, I think he framed it into the Clifford algebra terminology, which, if you view it correctly, is exactly the way I sort of mentioned it. But there have been other people looking at different action. It looks to me that the Zauner one is probably the most natural. I'm not sure. Maybe the most tractable one as well. And that might be why it sort of gained most prominent attention among people working in this.
I see. Okay, more questions. So another thing that I thought was that the dynamical sampling community will be probably delighted to see your talk, right? So because you can think of this as, okay, you have some operator. In your case, you take the Gabor action, so you have these two shifts. But in general, you can say, but can you take some A? Can you act with it on whatever the G was? And can you get something? Can you get completeness? So this is exactly, I think, what Akram does, right? So this is
absolutely yes, and yes, very, very naturally. And this is a little bit more concrete because I'm using just like a translation and modulation, but you might want to sort of see what happens when you take like different matrices, I guess. So I think the structure, the group structure, because of this is related to the Heisenberg group, play a lot of role here. So even if you give me like a bunch of over matrices, I guess it will come down to maybe, I don't know, what sort of algebra property the group will sort of, the set of the powers of your matrix will sort of generate. And that play a lot of role here because you're able easily, they do not commute, but most of the operation that I'm doing sort of ignore essentially the phase, because when you go to the Gramian side, you take the modulus. So therefore, you can sort of view this as sort of product of commutative matrix, essentially, which is, it play a big role. So I don't know if you just give me like a bunch of matrices, if I'll be able to sort of say as much as I'm able to say in this case.
Exactly. So yeah, so it will be really interesting. So if you, I don't know, if you are thinking about this already, can you do other pairs of matrices or something? But this is a really interesting direction there.
Yes, it is. I completely agree with you. Yeah.
Okay, so I keep waiting for this question from the audience, but it doesn't come, so I'm going to ask it. So I know Alexei also had some more recent results on 2-point distance sets with the Weishan Yu, I think it was. So yeah, so do you ever expect that these two distance frames are maximal two distance sets or something like that?
Okay,
yeah.
Yeah. So this is a lot more recent thing that I've because I didn't start we didn't start working on this with that in mind, but then we start seeing this example where there are only two values in this inner product, and that's when we start sort of. So we haven't sort of given like enough thought about like what kind of two distance we actually generating in this situation, and that's something that I'm not sure if it's going to be done in this project because it start coming out as we start sort of writing out many examples, and this might have to wait a little bit. But they seem to be very interesting two distance at the very least. I know they are not tight, because the Gramian, I know it has like, I can count how many eigenvalue it has, okay? And the eigenvalue are not all the same. But this is something interesting that I don't think I've given enough thought to sort of being able to put in a broader perspective.
I can comment a little on this.
Yes, please.
Yeah, so here the size is fixed. It's d squared all the time.
Yes, d squared all the time.
So and this is very unlikely that it's the largest size for a given dimension, because the bounds, so the upper bound is d to the 4th power around that.
Okay.
And I think there are constructions that are larger than d squared. I'm not 100% sure. It's in all dimensions, at least for real cases, because here we're talking about the complex case. It's a little different.
Yes,
but
yes.
This is going to be very unlikely. It's a lot. So, but it's a very interesting construction either way. So, just not
The thing is,
that
yes,
problem.
exactly. And I believe you can still, so the example I gave in 3 dimensions for this sounder, that's the vector that's complete but is not symmetric, you can embed this in like higher and higher dimension. So when you start embedding this in higher and higher dimension, you don't get necessarily completeness of those in higher dimension, but you still get things that are just sort of too distant all the time. And the distance are more or less fixed. So that's, I mean, we haven't thought about that direction a lot. So I'll have to reserve my comment until we do a little bit more about that.
Great, thank you both. Yeah, this is interesting relation. Okay, more questions, comments. Okay, so our audience is shy, so maybe let's stop the recording. Ryan, how about you go ahead and stop the recording, and we have some questions.